Right, so for the second question, what is the velocity of a beam of electrons that go undeflected when passing through important perpendicular electric and magnetic fields of those two magnitudes? Right, okay. So first thing we do is we have to understand that this means that the electric and magnetic forces must be in opposite directions and cancel one another. Now, just quickly go over that. I've got an electron moving in a certain direction, and it's entering a region where there's both an electric and magnetic field present, but it doesn't get deflected. Okay, now suppose there is a magnetic force. It doesn't have to be one, but suppose that even if the electron is moving, but suppose there is one. An important property of the magnetic force is that it's perpendicular to two things. It's perpendicular to the direction that the charge is moving in, and it's also perpendicular to the magnetic field. So that's very important. So if there is a magnetic force on the electron, then it's going to be in a direction that is perpendicular to the direction of movement of the electron. But if it's perpendicular to the direction of movement of the electron, then by itself it will deflect the electron. So that, but if it's then we know that it's not deflected, then that means there has to be the other force, not gravity. Gravity would hopelessly too weak. There has to be the opposing force, the other force present. The electric force will have to be opposing and equal in magnitude and in the opposite direction. Otherwise, it will get deflected. So again, if the charge is moving into this area of the magnetic field and the electric field, if there is a magnetic force on it, then for it to not be deflected, the electric force must be obviously in the opposite direction and with an equal magnitude. Okay, that is if there is a magnetic force. There doesn't have to be one. So for example, let's say the magnetic field is like this. And this is the line on which the magnetic field acts. Okay, now if the electron is moving along this line, so for example like this, then there won't be a magnetic force on it. There won't be. So if the electric force is also along this line, then the electron shouldn't be deflected then, because everything is just in the line, all the forces are in the line that it is moving in. Well, ignoring gravitational force, of course. Because that will just be too weak compared to the other two forces. Right. Okay, but the point here is that this is not possible, because the electric field is given to be perpendicular to the magnetic field. So there is an electric field and it is perpendicular to the magnetic field. So the electric field might lie somewhere like this, for example. Okay? And if it is lying like this, if this is the electric field, then this is electron, then there would be an electric force on the electron in that direction. Now magnetic force and an electric force in that direction, now pushing it out of its initial line of trajectory. So it will be deflected. So in the case where there's no magnetic force, so that would be if the electron's moving in the same line as the magnetic field, then the electric force, because the electric field is perpendicular to the magnetic field, as a given in the question, will result in the electric force deflecting the electron. So this case is not possible. But leaving the only other option where there is a magnetic force and it's not being deflected because the electric force is equal in magnitude but opposite in direction. So we start by making that observation. So 2. So the electric force and magnetic force on an electron must be equal in magnitude but opposite in direction. Okay. And this bit, that it must be equal in magnitude, that gives us an equation. So the two forces on an electron, the electric force and the magnetic force, must be equal in magnitude. Okay, so no arrows on top, so this is just the magnitudes that we're equating. Okay, so general formula for this, if you know what the electric field is that, and for this it's Q, B, sine theta, general formula for the magnetic force of a charge moving in a magnetic field with that velocity v, and theta the angle between the direction of movement and the magnetic field. Okay, so what we're after is the velocity, so that is just v is equal to e over b sine theta. Now, thinking back to this problem in the tutorial, I can't remember whether I talked about this sine theta. In fact, I think I might not have. I think I might just have written it like this, which would be the case if the velocity vector is perpendicular to the magnetic field. The reason for this mistake on my part is that this problem is based on a very good problem in the textbook, where it is explicitly stated that the direction of the electron beam is perpendicular to the magnetic field. That is an extra bit of given information, which I didn't include in the question. So strictly speaking, as the question is stated here, we can't fully answer it because we don't know what this theta is. So if a way to answer this question now without actually changing the question itself is, well, you can say, well, if this is now the formula for the velocity, right? So if for example, the direction of movement of the beam, so the velocity vector, if that is perpendicular to the magnetic field, as was given in the textbook problem, you can go and look for that textbook problem. If, for example, this is true, or you can put in any other theta, if, for example, this is true, then v is equal to e over b sine 90 degrees. It's just e over b. And let's substitute those values. So this is 8.8 times 10 to the 3 volts per meter over 3.5 times 10 to the minus 3 Tesla. Okay, so let's calculate that. So 8.8 divided by 3.5 times 10 to the power 3/6, good, like that. So that is, I'm going to provide two significant figures, so that's 2.5 and 246 times 10 to the 6. Everything is SI units, so this will also work out as SI units for velocity, which is meters per second. There you go.